to our session today for physical sciences. My name is Themba Ncube. Today we actually exploring an exciting aspect of magnetism, which is the magnetic fields. So in the previous sessions we've spoken about, the forces that exist between poles of magnet, in terms of attraction and repulsion. But today our focus is purely on, the magnetic field, as to say, okay, around the magnet, what exists around the magnet, and also how then do we prove that there is actually a magnetic field, and maybe by looking at the effect of the magnetic field on other magnetic materials. We'd also take a turn to look into the Earth, because we want to think of the Earth as a huge magnet, and we would want to explore as to what is exactly the science behind the Earth behaving like a huge magnet, right? So without much further ado, let's look at the mind map, or the concept map in terms of the concept. So what do we know already by now? We know that there are magnetic poles, and we're saying that every magnet is actually a dipole, and the dipoles, that's where you have got the north and south, attraction between opposite poles, and repulsion between like poles. So our focus for today is on the magnetic fields, and to see how magnetic materials are actually affected by the magnetic field. We already know something about the origin of magnetism, to say the magnetic domains in terms of the three ferromagnetic elements, okay, all right, which is iron, cobalt, and nickel. We'd also take a time to look into the Earth's magnetic field, because the Earth, again, in itself, the Earth is another dipole. And why does the Earth actually behave as a huge magnet, and how does this actually help us to sustain life on the surface of the Earth? Because there are a lot of implications as to why the Earth is actually a magnet, right? Okay, so the thinking today in today's lesson is actually about the following. Have you thought about how do we know that a magnetic field is present? How do we see a magnetic field, or can we see it if at all that is possible? And then if not, how then do we show that a magnetic field actually exists? And then the second question says, how magnetic fields make life on Earth possible? So it means if the Earth was not like a magnet, then maybe life wouldn't be sustained on planet Earth, right? Okay, now the keywords. It's very important. If you think of the keywords in terms of the terminology, it's all or nothing. Now, the terminology, actually, because science is a language on its own, the language that we use in science, as you realize in today's discussion, that the context of the words or the terminology will always differ. Or in other words, the meaning will change with context. So what are some of the key terms that we shall use today? We've got a compass, which is actually a simple magnet, which is a free-hanging magnet, okay? So we can think of a compass as a device, right? We'll talk about why we think a compass is a device. And then this is the magnetic field, which exists around a magnet, okay? This is, it exists around a magnet. We'll talk further about it, okay? It exists around a magnet, okay? Right? That's the term magnetic field, right? What else? We've got the magnetic poles, which is the north and south. And then while the magnetic field is around the magnet, it means the magnet is north and south. It's got north and south poles, which we would describe as the dipole. And then we talk about the Earth's magnetic field, because the Earth has a north and south pole as well, right? And why the Earth behaves like a magnet. So the Earth is another dipole. Okay, now let's unpack or break down the terminology. What is a compass? A compass is a free-moving magnet, and every magnet has got a north and south pole. So a compass is actually a device which is actually, in principle, a free-moving magnet which has got two poles. Hence, we'll think of a compass as well as a dipole. So the magnet, if a compass is constructed in one of the challenge activities, we would have discussed how to make a simple magnet at home. So if you take a simple bar magnet like this one and you hang it on a stand, on a thread, this magnet will actually start to move. As it moves, the North Pole is seeking the South Pole, and the South Pole is seeking the North Pole. So when this free hanging or free moving magnet comes to rest, the North will point in the South direction. Why? Because the North Pole is attracted by the South. We've spoken about the interaction of opposite poles, okay, in terms of the attraction, while the South repels the other South. So when this magnet comes to rest, it will actually lie in the north-south direction, okay? Right, so one of the pole will point in the geographic North Pole of the Earth, while the other one points to the geographic South Pole. Remember, the geographic poles are very important, guys. If you think of it in terms of when you allow a compass needle to move and come to rest, the north will point to the south, okay, while the south will point to the next, for a simple reason, because opposite poles, they attract. So there's a difference between the geographic north and the true north. It's something that we'll discuss, which is quite an interesting scientific fact, which is why we said earlier that the language it also is influenced by the context. So some of the meanings, when you say this is the South Pole, what do you mean? It's actually the North Pole. Why? Because the compass says north, but the north is actually pointing to the South Pole due to the nature of interaction of opposite poles, right? Okay. Right, so what is a magnetic field? This definition is very, very important. You need to go back to the examination guidelines, okay? Right, because this is where we extract all our definition. So this document, very, very important, because when it comes to definitions, it has to do with recalling. It's either you remember or you do not. So when you talk about the exam guidelines, that's our main source of reference in terms of definition. Keywords, pay attention to the keywords, okay? And the other thing that we've also mentioned about definitions is that they must be used in the correct context, okay? So when I read the definition, it must carry the correct scientific language, and it should convey the correct meaning, right? So they must be used in the correct context. Knowing the keywords alone is not enough. And when it comes to definition, it's all or nothing. So a magnetic field is a three-dimensional region in space. This is around a magnet in which another magnetic material or a magnet will experience a force. Now, let's break it down. So suppose we've got a magnet. Around a magnet in all planes, left, right, up, down. That's what we mean by three dimension. There exists what we call a magnetic field. So a magnetic field around any magnet is actually in three dimension. So such that in this space, if we place a magnetic material or another magnet, it will experience a non-contact force of what type? Of a magnetic nature, okay? So different types of non-contact forces. We've spoken about electrostatic forces being non-contact. We also know that the gravitational force is also a non-contact force. But in this case, we're specifically referring to the magnetic force. So a three-dimensional region in space, this is due to the magnet. So what creates the magnetic field is actually a magnet. Okay, because you cannot separate a magnet and its magnetic field. So the magnetic field exists as a result of the magnet. So such that if we place a magnet or another magnetic material, it will experience a force, and this force is a non-contact force, right? It's a non-contact force, it's a field force, as the name suggests. Now for us to look at the simulation, which shows the magnetic field around a magnet. And then one of the big questions that we asked ourselves is, how do we know that a magnetic field exists around a magnet? Because we can't see the field, but we can talk about the effects of the field. Now, what we have here is a simple bar magnet, right? So around this bar magnet, it shows the direction of the field. And you see that the field is from north to south. And then one of the things that's very important is that you need to realize that the strength of the field how strong the field is depends on the density of the field lines. It's something that we'll talk about later. And we want to also show that if a stronger magnet is used, say we vary the strength, the field even becomes correspondingly stronger. Now also you'll realize that the density of the field is greater at the poles, which is a suggestion that the field is actually stronger at the poles. So even if we move the compass, it will still rest in the north-south direction. Irrespective of where you place it, it will still point in the north-south direction. Okay, let's move it to the South Pole. It shows how it is. So there's a north and the south seeking pole on the magnet. Okay, so even inside the magnet, you'll see that the field is there in terms of the north-south. Okay, so we can even change that. Okay, let's go back to our slide. So that's the magnetic field as we have demonstrated it using the simulation. Okay, right. And then once again, the observation of a magnetic field around a bar magnet. Okay, so we've realized that the direction of the magnetic field is given as the direction in which the compass needle points, and the direction is such that it's north to south. Okay, it's supposed to be north to south. Okay, the direction of the field. Okay. Is north to south, right? That's the main idea, because in the field, you experience a force. So the reason why we talk about direction of the field is because a magnetic force is involved, and we agree that a force has got both magnitude and direction. So a force is actually a vector quantity. Okay, so if a force is a vector, it means we want to emphasize the importance of direction in the field, such that if we place another magnet, that magnet would actually experience a force, right, in a particular direction. Okay, so the magnetic field outside the magnet is from the north pole of the magnet to the south pole. So it's both inside and outside. Just to go back to the simulation, you'd realize outside the direction is north to south, and even inside you can see the direction of the field is still consistent as well. Right? And then, having said that, also, the magnetic field inside the magnet is from the south pole of the magnet to the north pole of the magnet. Okay? This is an observation, right? And then the field pattern is shown by ion fillings of a magnetic material. Now, why ion specifically? Remember, ion is a ferromagnetic element, right? So it's easier to use ion to show the field because ion is a ferromagnetic element, right? So this is a demonstration that maybe you can even do at your school or at home to show that a magnetic field does exist around a magnet, because a pattern will actually be observed. Okay, so this is what actually happens when you have ion filings. So ion filings is ion metal that has been ground into fine powder. So it will show the direction of the field around, as we have shown on the simulation there, right? Okay, so the observation of a magnetic field around a bar magnet, this is how you'd see it in real life, as shown using ion filings. And the reason why we choose to use ion is because ion is one of the three ferromagnetic elements, right? Okay, so representing the magnetic fields, we must draw the field lines to show the direction of the field. Okay, so we talk about the field lines. So these field lines are actually imaginary. Okay, they are from north to south in terms of direction, and these lines, they actually do not cross each other. Okay, the field lines touch the surface of the magnet, so it means it is perpendicular to the surface of the magnet. So in our representation, it's also important for us to actually show that. Okay, right? So this is the actual representation of the magnetic field lines around a bar magnet. But remember, the field in reality is actually three-dimensional. So this is just the representation of the field that exists around a bar magnet, which is a dipole, which has got the north and the south pole as well, right? Okay, So where the field lines are closely pegged, this has to do with the density of the field lines, right? This has got to do with the density. Okay, so where the density is greater, the field is strongest. We realize that it's at the poles where the field is actually the strongest. So where the field lines are separated apart, the field is weak. We're still talking about the density of the field as well. So a magnetic pole is a region where the field is strong. Okay, that's the main idea. Now let's look at the magnetic field lines, or the pattern how we represent it in terms of two magnetic poles interacting with each other. In this case, we've got two opposite poles, all right? And what do we know already about opposite poles is that they actually attract each other, they exert a force of attraction on each other. Now, we've got the north and south. So the field lines must actually touch the surface of both magnets, right? So if the field lines touches this, we've got something like this, all right? So this is how the poles interact with each other. However, the direction of the force is very important. It's from north to south, north to south, north to south, right? So this is what happens when the poles interact with each other, north to south, right? And then we obviously have the field lines even on the opposite end, all right? Okay, which shows that there is actually a force that will be experienced by the what you call the poles of a magnet, and the direction needs to be consistent. It's north to south. Okay, from the north to the south. Okay, this is away. Okay, this is away from the north. So this is the representation of the field pattern when two opposite poles interact with each other. Also, there is a possibility that you have the north on the left-hand side and then the south on the right. It will still be the same pattern, however, the direction is what's going to change, but still it's going to be north to south. Now, let's look at a case where we have got two like poles interacting with each other. In this case, we've got two bar magnets, the north facing the north. So what's going to happen, these two, they tend to push each other away, right? So as they push each other away, we've got something like this, right? We've got something of this sort, okay? Okay, remember, the poles are strongest at, the field is strongest at the poles. And as you move further away from the pole, the field becomes weak. But what is missing here is actually the direction. So it's away from the north towards the south, okay? So these are actually pushing away each other. So in real life, you don't see these field lines because we're saying they are imaginary. So if they're imaginary, what do we mean by that? It means in real life, they don't exist. We can only see the effect of the magnetic field, but we cannot see the field itself. So such that if we place what you call a magnetic material in this field, it experiences a force in the direction that is actually indicated in this case. So as you can see, closer to the poles, let's say this is position X, and then this is position Y in the field. Now, point X is actually, if you place a magnetic material at point X, it experiences a greater force than at Y, because point X is closer to the poles, of which if you look at the density of the magnetic field lines, it shows that it's higher. That's where the field is actually strongest. So the field is actually stronger at X compared to Y, okay? So that's how we actually represent the magnetic field around, you know, two like or opposite. Remember, when we say like, it can be north and north or south and south, okay? And if it's a case of like poles, there are those two possibilities. And when it comes to opposite poles, it doesn't matter whether we say south and north or north and south, because order is not important. The fact remains is that any two opposite poles will actually exert a force of attraction on each other. Having said that, I think it gives us a better sense, right? Welcome back to our second segment. We're still exploring the magnetic fields. Now, we have said also that the Earth behaves like a huge magnet, and we want to explore, the thinking behind that and the science as to why exactly would we want to, describe the Earth as as a huge magnet, because it is also a dipole, and as a result of that, it means around this huge planet Earth, there is a magnetic field. And let's talk to, the science behind that. Okay, so we're still exploring the magnetic fields, right? Okay, so what are we saying? We are saying that the Earth is a huge magnet, okay? So these magnetic fields are actually not only around magnets, or the effect can be felt by magnetic materials in a magnetic field. We're also saying that the Earth has got its own magnetic field, okay? So remember, what is a field? A magnetic field is a region in space around a magnet, okay? So if it's around a magnet, and then we say there's an Earth's magnetic field, it means the Earth in itself is actually a magnet, okay? We'll try and explore some reasons as to why, or the science why the Earth behaves like a huge magnet. So the big question that we asked at the earlier stages of our session, we said, what is the magnetic nature of the Earth's geographic north pole? Okay, so this is the Earth as you'd see, as it is represented as a globe. It's one of the planets. Now, the Earth behaves as a magnet because the Earth in itself is a dipole. So the compass, what it does, okay, it shows the direction of the field, okay? So we've got the north-seeking pole and the south-seeking pole. Now, the axis of rotation of the Earth is kind of tilted in such a way that there is an angle of declination, okay? So this is the axis on which the Earth rotates. So when we talk about the rotation, we're actually talking about spinning about an axis. So as much as the Earth orbits around the sun, what is actually happening, it also spins about an axis. And remember, moving charges create a magnetic field, okay? Because in the core of the Earth, what exists? There are those ferromagnetic elements. And remember, once the charges move, then they've got these, we create what is called, which we call them the magnetic domains. So what these magnetic domains essentially do, they create a magnetic field, which is why we've got the north-south pole, and the Earth is actually a dipole, okay? Right. Having said that, let's look at the simulation that shows the magnetic field around the Earth, okay? Right, so if we are to look at the Earth's magnetic field, we would actually realize that we are saying that here is the layout of the Earth. Okay, let's show inside the magnet the fields that exist. As you can see, this is the South Pole at the top, and then the bottommost is actually the North Pole, right? So what is happening here, we can even show the field that exists around the Earth's magnetic field. And this field exists merely because inside the core of the Earth, there are those three ferromagnetic elements, okay? So, and again, you'll realize that the field is actually stronger at the poles. So the upper part of this, representation shows actually the South Pole. So the North Pole of the compass, it points to the south, which is actually the true north. And then it says to us that this field is just like a bar magnet. And if you can see, inside this representation of planet Earth, there is actually a bar magnet which shows the north and the south pole, okay? Right, so that's actually the representation. And if we can go back to that, you'd realize that if this is our south pole, and then this is our north pole of the Earth, there is actually the magnetic field around the surface of the Earth, meaning that if you exert, you subject a magnetic material on this field, it will actually experience a magnetic force. So the direction is actually from north to south. That's the direction of the Earth's magnetic field as it is portrayed. Okay, right. Okay. So we've seen the simulation that shows how and why the Earth actually behaves like a huge magnet. So there's some of the observation on the Earth's magnetic field that are very important, okay? So a compass which is in essence a free moving magnet. It gives the direction of the field. And remember, the direction of the field is actually from north to south, okay? That's the main thing here, the direction of the field, because in a field, you've got a non-contact force. So the direction of the force, because force has got it's a vector quantity, it has got both magnitude and direction. So the direction of the field, okay, is actually is north to south, okay? That's the direction of the field, okay? So the north pole of the compass needle is attracted to the material at the geographic north pole, okay? So we talk about the true north and the geographic north, which is actually one and the same thing. And then it says the magnetic north of the material is that of the magnetic pole, or of south magnetic pole of that particular magnet, okay? And then, so the Earth's magnetic field is similar to that of a bar magnet, as we have shown earlier. If this is the magnet, this is the field that actually exists around this this magnet, because of the core of the Earth containing the ferromagnetic materials. So you get something like this, and the direction is actually north to south. So in this space, we have got what is called the magnetosphere, okay? So the magnetosphere is actually part of the atmosphere around the Earth's surface, which is actually due to the Earth's magnetic field, okay? So the magnetosphere, the magnetosphere actually arises as a result of the Earth's magnetic field, all right? Okay. So in this space, if we place any magnetic material, it will definitely experience a non-contact magnetic force. So we're still consistent. We do not see this field. Actually, what happens is we can actually see the effect of the field on other materials. It could be magnets, other magnets, or other magnetic materials, because we've discussed the physical properties of materials, okay? Right, so that's very important. Now, let's talk about the origins of the Earth's magnetic field, okay? The Earth's field is produced by the materials in the molten core. The materials here, we are actually referring to the ferromagnetic elements, okay? Because these are the materials that give rise to the magnetic properties. So these are ferromagnetic elements that we talk about. Okay, we have listed them here, that it's cobalt, nickel, and iron. So it's a combination of these three ferromagnetic elements that gives rise to the reason why the Earth actually behaves like a huge magnet. And as a result of that, the Earth becomes a dipole, okay? It becomes a dipole. But there are a lot of we can talk about the functions or the significance of why the inner core of the Earth actually consists of these three elements that we have mentioned, and describe them as ferromagnetic elements. Because it says to us, we need to understand why are these ferromagnetic, because the movement of the Earth in itself creates a magnetic field because of the three elements. And wherever there is moving charge, there is actually a magnetic field that is coupled to that, okay? And then let's look at the functions of the Earth's magnetic field. There is a huge significance in terms of protecting human life, and for the reason why actually life exists on planet Earth. So one of the reasons is the protection from high energy electromagnetic waves, okay? Now, we know something about electromagnetic radiation, which consists of, which is, self-propagating type of a wave, in such that there is an oscillating charge. And once the charge oscillates, it creates both a magnetic and an electric field that are perpendicular to each other, okay, which moves at a speed of light, which is like 300 million meters per second. That's how fast electromagnetic waves move. Now, what's the main source of electromagnetic waves? It is the sun, okay? So the Earth, in an effort to try and preserve life and protect life on its surface, there is a magnetic field such that when these electromagnetic waves actually are radiated towards the Earth's surface, they are able to be deflected by the Earth's magnetic field so that it protects. Remember, one of the main properties of electromagnetic radiation is that they consist of charged particles, high energy. Some of them we would refer to them as photons. So these high energy can be, essentially dangerous. So as a result, the Earth's magnetic field kind of deflects them. So when it deflects these solar winds, in a way, it protects, life that exists on the surface of planet Earth. So these are the solar winds, which consist of high energy particles. Okay. So these high energy particles are electromagnetic waves, which sometimes we refer to it as radiation, okay, which can be destructive depending on the amount of energy that it carries. So when if this is the surface of the Earth, okay, and then what you have here is the Earth's magnetic field, okay. So what this Earth magnetic field does, it deflects these solar winds, okay? These high energy particles, which can be potentially dangerous, then once they do that, in a way, it protects the Earth, okay? So that's one of the functions of the Earth's magnetic field. Not only does the Earth behave as a magnet, there's a reason why actually it shows those characteristics, okay? Now, one of the other functions, it has to do with the guidance of migratory birds and animals. The sense of direction is, in everyday life, it's something that's often chaotic. You often wonder why migrating, birds move from one pole to the next without losing that sense of direction. It is because they have in their heads they've got these three ferromagnetic elements. So the reason why, as they move, they are able to locate the intended destination is because, again, the Earth is a magnetic field. So the sense of direction is easy to be maintained while they migrate from one pole to the other in search for shelter. It could be food, maybe a change of weather because seasons change, okay? So that's one other biological significance of the Earth's magnetic field. It helps migrating animals to locate their sense of direction, okay? Right, and then one of the phenomena, this is just an observation, which is a result of the Earth's magnetic field. When light from the sun comes towards the surface of the Earth, so the Earth's magnetic field reflects some of those high energy particles, which are often absorbed by, molecules such as oxygen gas, nitrogen gas. These are actually some of the components that make up the air, okay, all right? Because the air is a mixture of gases. And then when these particles absorb these energy, they become excited. And when they release that energy, there is an observation of what is called the northern lights or the aurora borealis, which is a magnificent, display of brilliant colors, red, green, yellow, purple. This is observed, especially on the North Pole. But we also have the other one, which is the southern light, okay? The southern light is obviously observed in the opposite, pole, okay? So this one is called, the southern light is often referred to as the aurora australis, okay? So that's just the name that describes that phenomena. So these are some of the very important applications or functions of the Earth's magnetic field, okay? So not only is the Earth a magnet, but there is a significance or a reason why it behaves the way it does, okay? Having said that, let's take a short breather. In our third and final segment, we shall explore more concepts around the Earth's magnetic field and magnetic fields in general. Let's take a short breather for now. Welcome back to our third and final segment. We're still exploring the magnetic fields, and we've also indicated the fact that the Earth is, you know, a huge magnet. The reason for that, we've mentioned that, okay, it has to do with the composition of the Earth's inner core. So the three ferromagnetic elements are a reason why the Earth is actually a dipole, okay? That's why we have the north as well as the south pole. And as a result of the Earth's rotation, which has to do with movement, remember, once there's movement of charge, there's a magnetic field that results, okay? Now, we want to further explore, you know, the Earth's magnetic field, but what do we know by now? We know what a magnetic field is all about in terms of, you know, the Earth as well as a simple magnet. We also think about a compass as a free-moving magnet, which also has got its own magnetic field. Now, we understand generally the occurrence of the magnetic domains based on the three elements, Fe, which is iron, cobalt, as well as nickel, okay? And then we also appreciated the fact that the Earth's magnetic field plays a very, very pivotal role, you know, in protecting, you know, life on the surface of the Earth in terms of the solar winds, you know, which contain high energy particles. And the role of the Earth's magnetic field is actually to deflate those high energy particles, which could be potentially dangerous. Okay, so this is pretty much the focus that we have managed to actually assume for the purpose of this session. Now, let's look at some of the applications, because in science we talk about physical properties of materials and how that justifies their everyday use. You know, take for argument's sake, you know, if you talk about, you know, a material that is light in density, like aluminium, you know, as an example, you know, it actually is used to manufacture aircraft bodies. Now, that use is actually informed by its physical properties, that it is a strong material which is low density and it is lighter. Okay, what about magnets? In terms of application, what are some of these ideas that come to mind in terms of their application? Okay, the common uses of magnets in computer hard drives. Computers have become, you know, in this age, a necessity. You know, we cannot do without computers. Okay, our phones, they contain computers, you know, they're embedded with computers. And as a result of that, these hard drives, they contain magnets because of their uses in computers. So these are computer components or the hardware that we find in computers. Okay, that's one of them. And then speakers contain magnets, okay, because where there is supposed to be, remember what a speaker does. A speaker is actually a resistor which transforms electrical energy into sound. So that transition of energy transfer is done, you know, in the presence of a magnetic material, because there needs to be a magnetic field. So there are different types of magnets, and their uses will also vary from one context to the next. Okay. Then the other one is in the scrapyard. But in the scrapyard, we usually talk of electromagnets. Okay? We talk of electromagnets. Okay? One would assume that at some point, you know, in your earlier grades, you would have dealt with, you know, how to make an electromagnet. You just take a iron nail, and there's a reason why iron, because iron is a ferromagnetic material. So if you take an iron and then you wound around it, you use a copper wire, which is a good conductor. So the copper wire is a conductor. The nail is made of iron, which is a magnetic material. And then you connect it and complete the circuit to a source of energy, which is a battery. Okay. So as the current is flowing through that conductor, it magnetizes the nail. So that nail becomes a magnet while charge is flowing through it. Hence, we call it an electromagnet. So that nail shows, or it displays, you know, the magnetic properties because of electricity. Hence, we refer to it as an electromagnet. So in scrapyards, we use for sorting metals. Okay. Okay. So there's sorting of metals. Okay, because metals are magnetic materials. Okay, because so these are magnetic materials, right? So what happens is there's a lot of electricity and energy used. So they sort out these metals using electromagnets. Okay, so that's one of the common applications. And then the obvious one that comes to mind, you know, the stickers on the fridge, okay? To put your note, your reminders, you use a magnet. But the fridge, the surface of the fridge in itself, again, is a magnetic material, okay? So what is actually happening here is that the magnet attracts, is attached to a magnetic material that makes the surface of the fridge. So there's actually a magnetic field that exists around that magnet, such that there's a force of attraction between the two materials, hence they come into contact. So we are saying that these are some of the obvious ones that comes to mind, okay? And then the most important one, at a later stage, we'll talk about electrodynamics or electromagnetism, you know, motors and generators, which are electrical machines, all right? So these electrical machines are actually have got a huge magnet. They cannot operate without magnets. So, you know, motors are used to, you know, use electrical energy so that there is mechanical energy, while generators, they transform or convert, you know, mechanical energy to electrical energy. And in both of these electrical machines, there is actually a huge use of strong magnet. And the other thing that justifies their use, which has got to be taken into account, is actually the strength of the magnet, okay? So stronger magnets are used in these electrical machines, which are motors as well as generators. So strength of magnets, it needs to be taken into account, right? Okay, so these are the most obvious one. Now, thinking beyond just the obvious one, you may also think about some of those that we did not obviously mentioned in terms of application. Think about some of the applications or uses of magnets in real life, okay? So there is quite a many. That is something that's to take home for you guys. And then in summary, what are some of these take-home, you know, facts that we managed to discover in today's discussion? Is that the magnetic properties of the is actually a result of the presence of the three ferromagnetic elements. Okay, so all magnetic materials they actually consist of iron, cobalt, and nickel. Okay. Even the magnets themselves, they actually comprise of those three, or a combination of the three. And remember, we know something about alloys, right? We know something about alloys, which has to do with what? Mixtures. So a combination of these elements actually can give rise to magnetic properties within a material, okay? So a magnetic field, by definition, okay, it's a very important definition that you need to actually understand it. It's the region around a magnet in which another magnetic material or a magnet or another magnet, it could be another magnet, okay? It will experience a non-contact magnetic force. So this magnetic force is essentially a non-contact force, okay? Right, so in this space, be it the Earth's surface, you know, be it around a bar magnet, be it around a horseshoe magnet, if around it there is a magnetic field. And we can't see the magnetic field because we've actually discussed the properties of magnetic field. Once again, if we go through them, we're saying these are imaginary, okay? They do not exist in real life. So we can't see the magnetic field, but we can actually observe the effect of a magnetic field on another magnet or another magnetic material. Again, the density of the magnetic field line is essentially an indication of how strong the field is, okay? And you'd realize that these magnetic field lines are actually closer at the poles than anywhere else around the magnet, okay? That suggests that the field, the magnetic field, that is actually strongest at the poles, all right? And then once again, you must remember that the like poles of a magnetic, of any magnet, they actually repel, while opposite, they attract. So this has to do with the interaction of the pole. So like we're seeing similar poles, north and north, or south and south, while opposite is north and south, or south and north. The order is not of importance to us, okay? Now, every magnetic material is a dipole, okay? This word, I think we used it once too often than others. What do we mean when we say every magnet is a dipole? we cannot separate the North from the South Pole. So in other words, the North Pole cannot exist in isolation of the South Pole or vice versa. What that means is if we've got a magnet here and we break it down into two parts, what results are two small magnets, okay? And in both cases, it's actually a dipole. So it means you cannot separate the North from the South or the South from the North, okay? That's what we mean when we say it's actually a dipole. And then furthermore, the magnetic field is strongest at the pole. This has to do with the density of the field lines, okay, in theory. So field line density, okay, indicates the strength of the field at a point, okay? Okay, so this is the field line density. That's very, very important, okay? Now, overview of what we have done in as far as exploring magnetic fields and magnetic forces. We know there are magnetic materials, okay, and non-magnetic materials based on the physical properties. And this is based on the origin of the magnetic field, meaning that the magnetic fields are a result of the three elements, okay, iron, cobalt, and nickel, right? And then the Earth is a dipole as well because the Earth behaves like a huge magnet because it's got the north and south, and the core of the Earth contains the same three ferromagnetic elements, okay? And then the magnetic poles interact with each other in terms of attraction, which happens with the north and south, okay? North and south, while it's repulsion between north and north, okay, as well as, okay, it's north and north, okay, it should be north and north, south and south. So these are like poles, while attraction is opposite poles. So this is the big idea in terms of these magnetic fields. So hopefully these discussions that we took on the different applications, you know, think about some of the uses of magnetic field. So there's a huge significance of why the Earth is actually a big magnet, or it has got a magnetic field. So these are some of the very, very important concepts that we took a discussion of. Hopefully some of these are discussions that we have, they obviously, you know, help you to discover some of the fundamental concepts as far as, you know, the physics that we talk about. Because of time constraints, that's all we had for today. From myself, Themba Ncube, is cheers and bye-bye for now.